What's up, people, and welcome to the second part of my PID controller demo slash tutorial. So in this video we're going to dive into the implementation of the demo. So go ahead and go to this URL right here. I'll also put it in the description of the video, and go ahead and git clone it if you're interested in checking the code out. So that is that. We're going to be using the Pygame implementation. It's pretty straightforward. You can install it using Python like this with pip. And if you intend to hack into this, you're gonna need to have Python 3, pip 3, and this Pygame and NumPy. That's what you're gonna need. That will also be in the README file, so you can check that out. So when you have cloned it, you'll see that there is this main file here, and that is the entry point for the application, basically. It's not that big. It's just around 125 rows, so it's not that big, right? So NumPy and math, I don't know, I don't think this is needed. Let's keep it there to be sure. We have a display, which is an object. We have a drone, which is kind of like an object, and we have something called an applied force. And for the display, you're going to have some parameters for the display. It's going to be 1024 pixels times 800 pixels, and you're gonna have the center point of the of this screen. Doesn't really matter. The background is just like some resource image from the resource folders right here. So then we're gonna have a drone that is gonna have also some size with height, an image which is also in the resource folder here, a position which is only the initial position, which is going to change over time, a history of the positions that it has seen, a length of memory, and a force that is going to be applied to it, the PID variables, the P, I, and D separately, and then something called a pull force, which is also going to be clear in a while, and the applied force, which is also going to be clear in a while, right? So that is what we have. And I think the easiest way for me is to just go ahead and run it, so you'll see what it actually do, because it's a bit abstract right now. So you just run it by Python 3 and then the main application, right? So when you start it up, this is what happens. I don't know what this is. Get the drone. It's a bit laggy on my computer. I'm not sure why. And you see there is a ring here, and if I right click somewhere along here, the ring is placed there. You can also see that there is this red line following my mouse, and it's connected to the drone. That is a vector, and that is the applied force vector. So you see there is a vector here following along. So now it's really small, and now it's really big. And if I do a left click with this, when it's, for example, small, it's going to apply that force to the drone, like we did in the previous video with the addition, right? So you see now it was a really small applied force. If I make this a little bit longer like this, it's just going to take off. It's going to be a greater force, basically. So the goal of this game or whatever is to make the drone go to this position where I have placed my marker, basically here, or it's really hard to get this to do it manually. And the applied force can be thought of as external factors like wind, or someone giving the drone a push, or something like along those lines, right? And you can see right now it just floating about. It doesn't have any free will to place itself on the marker. It's just going around, so the marker doesn't really do anything at this point. And if I close this down, you can also see that the applied force is printed out here in the dimensions. But if I take a look at the code and go to the top here, I can adjust this. So let's say that I want to apply some proportional force to this. Let's make it pretty small. It's like at 0.1. That is good. And save the file. Oops, save the file, and let's rerun it and see what happens. So now you can see that it is moving as before, but the difference is that it is moving actually proportional to this. So if I place my marker here, you can see the vector, right? Now it's going to slow down a little bit. You can see it's like maybe the proportional force was too small. You can see now it stopped. I'm not doing any clicking here whatsoever. I'm just holding my mouse here so you can see the vector. Because this vector is what is going to be linearly combined, proportional only at this case, to the position of the vector, meaning that it's going to try to find the position, right? But it's a bit slow, so let's make it faster. Let's give it a greater proportional force, like maybe I'm not sure, maybe 1 point something, 1.0. That's good. And rerun it. It's still a bit slow. Let's make it something more effectful, like 5. Yeah, I'm not doing any clicking at all. So you can see here now it's trying to find its way to this position with the marker, but it's overshooting like all the time, because what it is doing is calculating the distance to that position and just like, you know, setting its force towards it, and then as soon as it arrives at that proportion, it has too great of a speed, so it just overshoots all the time. And that is the problem with the proportional force that we are applying. That it doesn't have any concept of, you know, how fast am I coming in towards this point, right? But there is another variable that does that, and that is the derivative force. And that the derivative force can calculate how fast are we approaching no error, and in this case no error means being on the position, on the marker. So let's go ahead and try that out and see what happens if we let's give this let's give this a little bit more, like 10 maybe, so it's a bit faster, and then we do the derivative also 10. And now if we run this, you see it's like, is it gonna get there? It probably will get there in the end. It's closing in, right? It's getting less and less error here. I'm not doing any clicking. It's closing in, but it's like oscillating around it pretty much, you know, it's going back and forth, but we can definitely see that eventually it's gonna get there. But it is taking a lot of time going back and forth, right? It doesn't really know that in the past that it has overshoot, it constantly keeps on overshooting it. And that is why it's like so slow, like oscillating towards this. And if I place my marker here, you can see that it's like, now it's trying to get there, and it's taking a lot of time to get there, basically. So that is what the integral part here is doing for us. It's basically, it's the heuristics of, in the past, I know that I have constantly overshot my position, so let's not do that again, basically, if you want to sum it up in words. And since I've tested this, I know, let's give it a little bit more derivative and test that out and see how it behaves, basically. So I don't want to sit here and watch it all day, right? So let's give it a little bit more force, so it's a bit faster. You can see that's, yeah, it's better, but still it's overshooting it and oscillating it back and forth. So let's give it a little bit of integral here and see how that is working out for us. Maybe it's overshooting it once. It's overshooting it once. And you know, you can like test this out. I don't know if this is the best parameters picked, but it's, I mean, when I watch this, it kind of feels like, you know, how drone works in a way. It feels like, yeah, it's, you know, it's going in really fast, and then it's like maybe overshooting it, but it's correcting itself with the integral there in the end, and then it's like, yeah, it's getting there, basically. Intuitively, I feel that this is kind of how they move in the real world from the ones that I have seen. And yeah, let's simulate what happens, how it's behaving. If I start clicking them and pulling them, like, you can see that now it's working pretty well when I pull it like in some other direction. and apply some force to it externally, it's like correcting its way there. So that's kind of cool, I think. I think it's super cool. You can definitely see how you can apply this to real-world applications. Of course, with the real drone, you would have another dimension, the Z dimension, the height. But the implementation would actually be, I mean, exactly the same. But just with like an additional, dimension. And then, of course, you have to test it out so it doesn't crash, and But that is that. I think I'm gonna pause the video here for the ones that are interested in just like the demonstration, and for the ones that are actually interested in the implementation. In the next video, I'm gonna go through all these functions and see how this is implemented, and for the ones that are interested in this, how these are actually calculated, the PID variables and stuff. So I hope you guys enjoyed the demonstration, and don't forget to subscribe if you haven't already, and I will see you in the next video. Bye bye.